So how do you quantify the fatigue behavior? Okay, for example, yield strength, how do we quantify? By conducting a stress and tensile test or compression test by drawing stress strain diagram. From that you can get the yield strength and other parameters, right? Similarly, even for the fatigue test, okay, fatigue uh, strength, okay, what we do is we conduct a test. In fact, it is a collection of tests, okay, by taking number of samples, okay, by uh, uh, varying the stress amplitude. Okay, in the previous case, if you see, you have seen the kind of stress cycle, right? If you see, we have something called amplitude here, right? What is this stress amplitude? Okay, or here it is maximum stress. It is maximum stress. This is the quantum of stress is amplitude is this much, and what kind of stress? It is tension compression. It is tension. This is a spectrum loading. Okay, it's a very irregular loading, so it may behave differently, or it may have different fatigue strength based on what kind of load it is. Okay, it may, if it is tension compression, that is opposing loads, okay, a reversal, stress reversal is there in the cycle, it may have a different behavior. If it is only tensile but varying load, it may have a different behavior. And similarly, if it is a complete random, it may have a different behavior. When I say different behavior, it may last for based on what kind of load, it may last for a different uh, you know uh, life or lifetime. Okay, some samples can withstand 1 million cycles, okay, cyclic load. Some samples can withstand 1.5 million cycles load. It all depends on, as I said, whether it is belonging to what type of cyclic load. Okay, the way they are portrayed in this particular slide. Okay, now assuming any one particular, we know the application. Okay, based on the application, we know whether it is a stress reversal, or stress tensile compression, or only tensile, or it's a random. That way you can figure out what kind of loading this material may be undergoing. Okay, now once you fix the type of loading, now how do we, okay, arrive at a particular fatigue strength of a material or fatigue limit? By conducting different tests. In each test, you will be varying the stress amplitude. Okay, that you have seen in the diagram. The amplitude of the stress you will be varying and conducting different tests. So what is happening here? If you apply very high stress amplitude, this is stress amplitude, right? The material may fail very early. Okay, with very minimum number of cycles. Okay, this is number of stress cycles. That means higher the stress amplitude, you have very less life. Whereas as you keep reducing the stress amplitude, you see the life is gradually increasing. You see the curve is moving the right side. That means you have more, it is able to sustain more number of cycles, right? So you see there is a linear curve here. That means there is a point where until which you actually have a proportional life. Okay, that means lesser the inversely proportional, lesser the stress amplitude, higher the life, and it is a linear relationship in this particular case, which is need not be the case always. Okay, now there is a particular point, that means there is a stress amplitude below which if you apply, okay, the stress, the material is not failing, it is going forever, right? Below the stress, below that stress amplitude, for example, if you apply only this much of stress amplitude, you see the material is not at all failing, right? That means it is not failing, it can take infinite number of stress cycles, it is going, right? So this particular point, okay, up to here you have a finite number of cycles for which it can sustain the loads, but below this stress amplitude it can take up infinite number of stress cycles of that amplitude. So what we call this particular point, at which it can take infinite cycles, cyclic load, we call it fatigue, okay, limit. Okay, we call it fatigue limit, which is also named as most popularly it is also called as endurance limit or fatigue strength. So fatigue strength, like the way you have for gradual load, you have yield strength, you have fatigue strength, You have endurance limit, you have fatigue limit. All these represent the stress amplitude at which the material can sustain for infinite number of load cycles. Okay, that is the meaning of that. So our aim is to draw this particular SN curve. S stands for stress amplitude, okay, and N stands for number of cycles. So this SN curve will actually determine its fatigue strength of any material. Okay, and you have to conduct, you have to get this, you will get this line by taking different samples and conducting test at different stress amplitudes. Okay, here 1 2 3 like that. Okay, so many samples. Okay, yeah, now if you see the actual curve for a particular material, so this is typically a steel, an aluminum alloy and a tool steel. Okay, you can see it's non-linear. First of all, second thing is, at any given point of point on the SN curve, you would know how many cycles. Okay, for example, here it is 1 lakh cycles fatigue, life will be there if you apply this much of load. Okay, it is in psi, you can change it to SI units. In any case, for a particular load, how many cycles it can last is what it will give SN curve, right? And of course, if you further reduce the stress amplitude, there is a place, there is a point where endurance limit, beyond which it can sustain for longer or infinite number of cycles. Okay, that is what we call endurance limit. Similarly for aluminum alloy, of course aluminum has less yield strength, so it will also has less yield, less fatigue strength. Okay, so that is a material behavior. Okay, right. So next one, one important mechanical again measure or mechanical property is of a material is creep. Okay, what is a creep? Creep is nothing but the failure of a material, okay, under a constant load. That means you are not applying, increasing the load or decreasing the load. Under a constant load, the material creeps or fails with time. Okay, at elevated temperatures. I repeat, the failure of material, okay, with time, okay, at elevated temperatures, under load, under constant load, okay, is called creep. Okay, can you imagine this? For example, you have a bridge. Okay, assume some people have not considered the creep, and of course, so they have designed it faulty, with faulty parameters. So what happened? The bridge itself is heavy in weight, right? So assume you haven't considered it. Okay, because the bridge has to withstand, first of all, its own load before carrying any other load, right? So what happens with time? Now the load is constant, the bridge weight is constant, right? Under constant load, and assume the temperatures in the surroundings are very high. Okay, so what can happen? The material can slowly deform, slow and progressive deformation can occur. Okay, because the load is constant but temperatures are high, so material behaves slightly differently. So it will start deforming slowly. Okay, and finally what happens? There will be a point where you will have small voids that are formed within the material, and these voids get agglomerated or gets accumulated, and finally you will have a cross section which is critical. Okay, the cross section gets reduced with time, right? As the voids form, finally the cross sectional area will become so small that it cannot bear its own length anymore. So there will be a sudden failure finally. Okay, but before that you have a slow and progressive deformation. Okay, so yeah, all this behavior we call creep behavior of the material. Okay, how it deforms, how it behaves, okay, under constant load with time at elevated temperatures. Okay, so now you understand how important it is, okay, based on the example that I have given. Now again, we have to, any property that we think of, we have to quantify it, being engineer, right? Fatigue behavior, we have to quantify it, we did it. Okay, yield strength, we have to quantify it, we did it. Similarly, creep behavior, we should be able to quantify it so that we can design, okay, components keeping your creep behavior in view. Okay, now how you quantify the creep material for creep, or how you quantify the creep behavior of a material? So again you have to conduct a creep test. Okay, how do we do that? We'll take a sample and we apply at elevated temperature a constant load, and we see how it is deforming with time. Okay, and if you see the creep curve, any creep curve of a material, it will essentially have three stages: 1, 2, 3, are primary, secondary, and tertiary. Okay, so primary creep are the first stage of creep where you have a positive slope. Okay, in fact it is negative slope. Okay, but if you see, it is a non-linear, okay, curve, isn't it? And also you see the material undergoing or material is undergoing strain hardening. Okay, that's what you see here. Okay, okay, it is the first the primary transient creep occurs first, typically by continuous decreasing creep rate. Okay, that is the slope of the curve diminishes with time. That is what I call negative slope. Okay, this suggests that the material is experiencing an increase in the creep resistance or strain hardening. Okay, so that is what happening here. Okay, strain hardening, right? And your slope increases, but the increase in the slope will be decreasing. Okay, it's a diminishing slope. Okay, right? So from this point onwards you have a constant slope. Okay, that is what we call secondary creep. And this is what, being a designer, you will consider for any material. Okay, what is the slope here? This is time, this is creep. Okay, strain rate, the creep strain with time. Okay? Yeah, so the slope here is what you consider for the designing of any mechanical component. Okay, for creep. Okay, and the tertiary creep. Okay, what we see at the end, as I said, as the voids get accumulated, the material will fail by rupture finally. Okay, which is again you cannot consider for the design application or the for the design purpose. Okay, right? So these are the different stages that I already explained, isn't it? So yeah, so let us move on to the topic called composites. So as we discussed in the classroom, the composites are the ones they exist because we want to fulfill that gap that is there because of non-existence of some of the combination of properties in the materials. Okay, for example, we discussed that you cannot have in a material, naturally occurring material, both ductility and strength together. Okay, usually if you have more ductility, you have less strength for the material, say aluminum and so on. Or if you have very high strength, you cannot have the ductility, sufficient ductility, say ceramic materials, right? So unfortunately, being an engineer, you know the importance of these two, and you want to have the characteristics of both. Okay, because your material should be tough as well as it should have sufficient strength. Okay, to have these contrasting properties together, you have to artificially synthesize, okay, some new materials. And one of such materials are called composite materials, and you can classify these composite materials based on the concentration amount of second phase, okay, the size of the second phase, okay, particles, or the shape of the second phase particle, or the fashion in which you have arranged inside, distributed, or the orientation in which the second phase is there. Okay, similarly you can also classify these composites by what kind of matrix you have, whether it is metal matrix or whether it is ceramic matrix or polymer matrix. All three of them are very famous. Okay, and you can have again a classification based on the reinforcement, whether it is particle reinforced or fiber reinforced, or it is just structural. Okay, and it's size of the secondary phase and so on. Okay, whether they are aligned or randomly oriented. Okay, all these things are very important. Okay, all these different variations will drastically change their external mechanical properties. Okay, and similarly we have something called rule of mixture that comes into picture when you talk about composites, simply because you may have aluminum with some graphite reinforcements. Now how do you know what is the Young's modulus of this material? By using the rule of mixture, you can have the effective Young's modulus by knowing the volume fraction of each of the phase.